Factors affecting the bond enthalpy. Okay, on what factors? Size of the bonded atoms and bond length. Let us see one by one. First is what? Size of the bonded atoms. Small size of the bonded atoms results in the formation of a stronger bond, signifying larger value of bond dissociation enthalpy. Means what? See, when the size is small, they go close. When they go close, strong bond is formed. When the strong bond is formed, we require more energy. For example, bond dissociation enthalpy of HH bond is 435.8 kilojoules per mole, whereas in the case of chlorine, bigger size, it is 243.5. This clearly tells that smaller the size of the bonded atoms, stronger is the bond, more close they are, more energy required to break. The bond length. If the bond length is short, close, once again close. Lesser the bond length, more close, strong is the bond. Value of bond enthalpy will be large. Same. For example, CC bond length is 154 picometers, is higher when compared to the C double bond C bond length 134 picometers. Okay, right. So when the bond length is more, they go far away, less attraction. So we require what? Less energy. Whereas C double bond C, the more close, less bond enthalpy, more energy requires. Okay, so bond length is short, bond enthalpy is more. Consequently, the bond dissociation enthalpy of CC bond is smaller compared to the C double bond C. Now, average bond enthalpy. Instead of going for the bond enthalpy, simply now today we are using what nowadays average bond enthalpy, average bond dissociation enthalpy. Why? Because see, we are learning not only atoms, molecules of the same element. We are also learning molecule from a different atoms. So HCl, Na2SO4, NaCl, H2SO4, HNO3. The time we don't use simply the word bond enthalpy, because in the HNO3, N is for example in the methane CH4, there are 4 CH bond, one CH, second CH, third CH, and 4 CH. So if one bond breaks CH bond, 3 CH are there. Again to break second bond and third bond and the final bond. So now totally we add and by number of 4 bonds, that is called average bond enthalpy. That is the idea of the average bond enthalpy. Okay, with example it is clear. Let us wait. In polyatomic molecules, the average of the bond dissociation is called average bond enthalpy or just bond enthalpy. Let's take a case of water. Okay, see, water, first we will break one OH bond. Okay, this is the energy. Then second OH bond 427. Why it is less here? Once we break the H, okay, then it is only OH. So OH is highly unstable. So with little less energy we can break the second OH. Now what is the average bond enthalpy here? To break the first OH, this much energy. To break the second OH, this much energy. So if you add these two and divide by 2, that is called average bond enthalpy of water. If it is only Cl, to break that bond, that is the bond enthalpy, because it is similar atoms. When different atoms have combined to form a molecule, the time separately will calculate, then add by the number of how much you have tried, that is the average bond enthalpy. The different values of average bond enthalpy concludes that the second OH bond undergoes some changes because of the changed chemical atmosphere. Okay, when we break one H from the H2O, now after removal of the H from the H2O, it is OH only, which is having different chemical atmosphere compared to the H2O. It is slightly unstable, so we require less energy. So depend upon the chemical atmosphere, after breaking the one particular bond, we have the bond enthalpy. This is the reason for difference in the energy of same OH bond. See, both are same OH only in water. So OH, two OH are there, but why different value? Because of what? Different chemical atmosphere. Same case here also. Here also one bond is there. But this OH bond is what with CH3 with different group, and this OH bond is there what with different group ethyl. So depend upon the OH bond with what it is there, that matters. That one I told you here, chemical environment, chemical atmosphere. This OH is with methyl atmosphere. This OH is with ethyl atmosphere, and in the water OH is with the H atmosphere. So depend upon the atmosphere what OH is having, bond enthalpy matters. Therefore, for polyatomic molecules, we use the word what? Average bond enthalpy. Even if you use bond enthalpy, no problem. But the more correct way is what? Average bond enthalpy. It is obtained as average of different bond dissociation enthalpies in a molecule. For example, water, I told already, both are taken and by 2. This is the average bond enthalpy of water. Thus, bond enthalpy is the average or mean enthalpy needed to break bonds of a given type in 1 mole of the gaseous molecules. That means to break 1 mole of water, we require 464.5 kilojoules energy. That's why it is called 464.5 kilojoules per mole. This is the average. This much energy requires to break all the OH bonds in 1 mole of water. Obviously, for diatomic molecules, the bond dissociation enthalpy is simply enthalpy because both are same, H, Cl, Cl. So they both are same. So there you can use only bond enthalpy. But for the polyatomic, average bond enthalpy for polyatomic, for diatomic, just bond enthalpy. Now we'll go for the final or the fourth bond parameter. Number of bonds between two atoms in a molecule is called bond order. How many bonds are there between the two atoms? That is the bond order. For example, bond order in H2 in which 1 electron pair is shared is 1. In O2 where 2 electron pairs shared is 2. And in N2 in which 3 electron pairs are shared is 3. How many bonds are formed between the two atoms? That is the bond order. In hydrogen, single bond is formed, 1 bond is formed. So bond order of hydrogen is 1. And in the case of oxygen, 2 bonds are formed. So bond order is 2. Similarly, bond order of N2 is what? 3 because 3 bonds are formed. So depend upon the number of bonds, bond order is there. Hydrogen bond order 1, of O 2, of N what? 3, and of carbon to O3, this is also 3. Okay. Now, one small extra idea. It may be noted that isoelectronic species have same bond order. What are isoelectronic species? Species with same number of electrons. See here, F2 and O2 2 minus. They are isoelectronic species because they have 18 electrons. But what is the bond order? 1 only. Why 1? Earlier in the O2 double bond was there. But after gaining 2 electrons, it will go for the single bond. So F2 already single bond is there. This has gone for the single bond. That's why bond order is 1 only. And in the case of N2, already 3 bonds are there. So bond order is 3. Here bond order CO, carbon monoxide, it is 3. Between the NO plus ion, triple bond is there. You draw Lewis structure, you will come to know. It is 3. So all these 3 have same number of electrons, but bond order also same. So I think today we discussed about the bond parameters, which is a very interesting chapter. So in the days to come, we will discuss 2 more small points, that is polarity of bonds and the resonance. This is all about the covalent bond only. I already told in the previous class that we learn more about the covalent bond. Okay.